Welcome to TutorialsArc, your go-to destination for unraveling the fascinating world of computer science and information technology. Whether you're grappling with complex concepts, seeking clarity on industry jargon, or eager to explore the latest emerging trends, you've come to the right place. We break down intricate topics into easy-to-understand explanations, making learning accessible and engaging for everyone. So, buckle up and get ready to expand your knowledge in the ever-evolving digital landscape. TutorialsArc, optimized for learners.
Welcome to Linux context switching. The Linux operating system is one of those operating systems that is known for its capability to handle multiple tasks, multiple processes at a seemingly concurrent time. So how does it do this? Context switching explains how that is exactly done. So what happens is, because there are multiple processes competing for the limited computing resources, in this case CPU time, the operating system has to improvise a means of allowing each of these processes take advantage of that CPU or central processing unit time. How is that done? It is through the process of context switching. So what the CPU does, or what the kernel does, or operating system does, is that it handles a task or a process, manages that process. After given duration of time, it saves information about that process, saves it somewhere, handles the next process, and the next time it comes back, it knows from what point it should proceed with the previous process. That is what we refer to as context switching. So how does this happen? We have, for this case, one CPU. That CPU has to handle those multiple tasks: task-freed, test-freed, chunk triton. So how will you do that? As shown by those arrows, it could switch from one process to another, from the other to the other, and back. That's what we're explaining as context switching. To illustrate, let's look at our diagram here. On your far left, you have process 0 or P0, and that vertical line is its timeline. On your far right, we have process 1. That vertical line, it's its timeline. This is an example of, in this case, only two processes, but we may have more than two processes. So process P0 will be executing as shown by that dark arrow. From the beginning, it was executing, but because of an interrupt or a system call, it will have to pause. So what happens? We come to the center. It saves all the necessary information that may be necessary should the CPU revert back to it at a later time. So what is that information that is saved? Remember, we're saying we are saving information about the process. Here it is being shown as save state into PCB0. This PCB is the process control block. Is the one that contains that necessary information, or those necessary information. So one would ask, what is the information that is saved? Think about it. This is a process running, and the next time we come back, we want to know where we stopped. So the first thing should be identification for the process. That is the process ID. It's a unique identifier for each of the processes. It saves the process counter. What was the next instruction we are just about to execute in that previous process? So that is the process counter will be saved. The CPU register, memory management information, memory located to that process. For example, the page tables. What about the accounting information? It's also saved. The CPU utilization, execution time, and so on. Each of these processes, a number of these processes may be depending on some external device or input-output device for it to run. So the input-output status information saves that. So having saved all this information, we go back. It has to inform the next process. In this case, our process number 1 says, yes, you can take charge of the CPU. And for it, what state does it go to? It becomes idle. When it's idle, other processes run, or the other process, in this case P1, will be executing. It will similarly execute as shown by our black arrow there. It executes until it receives an interrupt or a system call, or we could say its time slot is done. So what does it do similarly? It will also go back, save its information in process control block number 1 for process 1. It saves that information until it informs the next process. In this case, this is our process 0. Says, I'm done, please make use of the CPU. That process 1 will execute. After execution, it will hand over to the next process and to the next process, because we know we have multiple processes. So that is the aspect referred to as context switching. Because of that context switching, our processes will be in one of the following states. It's going to be waiting for it to execute, could be ready for execution, it could be running at a certain point in time, or one could have terminated it or stopped it, or it will be created. So what are these states? Just a brief overview of what the states are. The process can be, number 1, running. It means it's currently being executed by the CPU. If it's not running, it's possible that it's sleeping, or uninterruptible, which means the process is waiting for an event, is waiting for some resource. But take note, some publications will show you that there's also the stopped. If it is stopped, it means the process has been paused, usually by some signal. So we have put this together as two, have sleeping or stopped. Many processes, when they run, they create other processes or child processes. So when the child process runs, the parent process has information about the child process. However, sometimes for some reason or another, the parent process could execute, complete its work, and forget to remove information about the child process. So we see the child process remaining as an orphan. So that child process without the parent process is referred to as a zombie. So our processes can be zombies. And then we have number 4, it's idle. Idle is a state of the kernel where the process has no other tasks to perform. So these are some of the states that reflect the dynamic nature of our process management in Linux. We are showing this because logically it's going to result because of that process of context switching. So on our terminal now, our intention is to try to see if we can get information about the processes running on our system. Remember, one of the key features of our Unix operating system is its ability to handle multiple tasks, many processes. So the keyword, the command, or the Linux utility that will help us do that is the ps command. If I do a ps, it will give me a summarized information about the processes running. So when we click enter, yes, it shows us the process ID, it shows us the terminal in which it was run, the time, and the command name. So what was the last command we typed? It was ps. What was its ID? 74. The terminal used TTY1. But this may not be detailed enough for users. So through use of other options, additional options on the command, we can get much more detailed information about the different processes that are running. So we want to use the same command with the option UX. So we put ps space UX. We expect this to give us much more detailed information about the processes running. I click enter and that's it. It gives you the user who run the process, gives you the PID, it gives you the CPU utilization, memory, terminal used, start time, command name, and many others. So yes, through use of the PS and other commands, we can get information about the running processes. One thing that I wanted you to take note of also is the process ID for PS in this output. Our PS is right here. What's the process ID? It's 75. The previous process ID for PS was 74. So it shows us that this is a different task. So it's true, we can see the processes running at the different states in which they could be on our Linux machine. Let's go back to our slides. So that's it. In conclusion, our context switching in Linux is very crucial for multitasking, for multiple process management. It allows the kernel to efficiently share that limited resource, the CPU time, among multiple processes by saving the state of one process and restoring back that state another time, or restarting the next process until it reverts back to that process at a later time. Hence, context switching. That context switching has its advantage. It creates an illusion of concurrency, of concurrent execution of these processes, and literally, though, it is not they are not concurrently being executed. It's only that it enables very fast responsiveness and resource utilization. Thank you for watching. I hope this explanation can be helpful to you. Thank you.
Thank you for watching. We hope you found this helpful. We are always looking to improve, so please leave any positive criticism or suggestions for future videos. Are there any other topics, concepts, or terminologies you'd like us to cover in future videos? Let us know. And don't forget to subscribe for updates on new tutorials.